the collaboration between Fraunhofer and IBM, how this leads to a strong push for the quantum industry. Oliver, the floor is yours. Excellent.
So I will try to make 3 points during my presentation. One is I would like to explain the role and the organization of the Fraunhofer Quantum Computing Competence Network related to the questions, are we looking for cloud or modular computing system? Then I will come up with a new idea, what we are going to do together with IBM, which might be of interest to companies and university in Switzerland too. And then, because I'm a scientist, I would like to go into one cubic platform, which we call the spin photon-based quantum computing platform, because that is a platform which might be good for hybrid and distributed systems, which is complementary to what we see IBM is doing. And Jack, you mentioned the fun part in Rust, I guess, and I hope your kids were allowed to go to the Eurostar, and our Eurostar is the IBM Q System 1, which is in operation close to Stuttgart. So in principle, we have a kind of German quantum computing system which is working, and I will talk about that a little bit more, because that is a core of the Fraunhofer IBM collaboration, and the system is operated by IBM Germany, which is located close to Ehling, and we offer a cloud access. If you would like to have your own quantum computing system and you are in a situation where you have to buy it, I can tell you it's really expensive. So for a lot of SMEs and university, it's too expensive to afford it. So we saw together with IBM, we create a system where universities in Germany and companies can buy tickets. So in principle, we are selling tickets to users on a monthly basis so that they can have their first experience with an IBM quantum computer. So what Fraunhofer is doing is we organize as a kind of administrator an IBM quantum computer based on a leasing contract between Fraunhofer and IBM. And this model could be also interesting for other countries because I can recommend it. And it's not only the access to the local quantum computer, it's also accompanied by an access to the IBM cloud. You might know that IBM built already, I would guess, around 40 quantum computing systems working with different qubit topologies, advantages, and these systems are very good for learning. So if you would like to have a foot in the door and learn how a quantum computer is working, this is the best way to go. So we have that cloud access, and the administration is done by a Fraunhofer Institute located in Berlin, and we do it all. So we can provide an access that you learn the physics of the qubits working, as well as you can learn Qiskit on an online basis. So it's a good way to start and to become familiar with quantum computers. So if we use the cloud of IBM to Yorktown location, we can, by example, provide the Hummingbird system that is a quantum computer based on superconducting qubits, and 65 of that qubits are working, and the system has a quantum volume of 32. And the good thing is that the 1 and 2 qubit gate errors are in the range of 0.05% and 1%. So you can do, let's say, 100 quantum gates after each other and apply it on each qubit, and it's still a good result coming out of the system. And you see the topology of the qubits. So the connectivity of the qubits is not the best. That is a disadvantage from my point of view related to superconducting qubits. But what is very good is the operation time. So for the 1 qubit gate, it only takes 35 nanoseconds. And for the 2 qubit gate, 500 nanoseconds. Comparing all the qubit platforms I have seen, a big advantage of this system is that the gates are really fast. So in Inning, we have a smaller system in terms of qubits, and this system is, I would call, for a quantum computer, it's robust, yeah, in terms of what you can expect in error and what you can do. And it's good, very good for learning, for starting into the field. And you see the Falcon F4 qubit topology, which consists of 77 qubits, but it has also a quantum volume of 32. And because we are able, with the help of IBM, to improve the situation, we will increase the quantum volume soon. I come back to that later on. So we have structures, the competence networks into countries. That's because it's easier for us to raise funding for it. So at the moment on the Inning system, 14 universities have access within projects, 8 different scientific organizations, as well as 36 industrial partners. And what they're doing is education and training. That's very important. They learn about the performance of the computer, advantage and disadvantage. First steps of error mitigation is going on, programming with the help of Qiskit and runtime, and we create the first algorithm, by example, for quantum chemistry, material simulation, optimization, error correction, and it's going more into logistics and finances. So we try to be applied as good as we can. We have to admit, if you are looking for the best computer on the world, you are too early. If you are looking for a quantum advantage, maybe you are a little bit too early, but if you look at the IBM roadmap from Hummingbird to Eagle to Osprey to Condor, I think if you are interested to use quantum computer for your production or for your simulation, you have to start now, because the development is so fast that if you not start learning now to operate the system, at least that's my feeling, you might be too late. And to improve the situation in terms of quantum volume, beginning next year, we will improve the system in Inning to a quantum volume of 64. So the system becomes even more closer and closer to application and the first situation of quantum advantage. We started to talk with IBM if there's any chance to get access to the Osprey and the Eagle processor. And we are very hopeful that at least in 22, 23, so that means in 1 to 2 years, the number of qubits will raise to in the range of 400, and this will double the existing quantum volume 2 times by 2. So we have the feeling, at least in the fields of quantum chemistry, something like that, we are coming closer and closer to the situation of quantum advantage, and then the interest of the industry will increase exponentially from my point of view, and also the terms of data sovereignty becomes important. And that's one of our motivations, that we try to establish the cooperation with IBM in a way that we will have a German, at least a European quantum computer, where we can ensure that the data created in Germany and Europe will stay in Germany and Europe. And that might be of interest to the industry too. So cloud access is good. A single quantum computer nearby is good. But in principle, we have learned a quantum computer needs a classical computer, and it would be even nicer if we can combine it with other high-power computing systems. And we have the Forschungszentrum Jülich, very skilled in high-power computing, and they have already other quantum computers running, or they're very close to establish those systems. So what we are planning at the moment is if we can connect, let's say by a glass fiber, the system in Inning with other computers to see if we can do the first step and learn how a quantum computer can be combined with others. Because we had the feeling that the industry at the moment is not interested to use only one quantum computer. They would like to have access to many computers to learn what is the best system in the future for them, for which application. And from my point of view, in the next decade, there will be not the one quantum computer, there will be different systems with different advantages for different applications. And we have to find out what is the best system for which application. So we need the information from the industry, what they need, and we have to try to come close to the needs as good as we can in the combination of university, scientific organizations, and industry. That's what we do. And therefore, we have to easy access as good as possible. And by example, the latency time between a quantum computer and other computers can be important in the interaction. And therefore, we thought it would be a good idea to connect the IBM quantum computer by an optical fast network. And that's what we think of at the moment. Still, we will have the cloud access. So we will have two kinds of hybrid networking systems. And as I said, Jülich could help to check the quantum computer in combination with other computers so that we can talk about modular systems where quantum computer is one part of the system. In Germany next year, there will be at least starting 8 consortia which are developing different qubit platforms with different topology. And what we like to do is to benchmark these developments. And therefore, we think together with IBM, if we can create a test and application center in Eningen, and that we offer on a nearly perfect objective basis, that we benchmark the systems. And it's also important to find out how we can benchmark the systems. And I guess, as I said already, we have to benchmark the systems in terms of the applications where these qubit platforms are optimized for. So we are looking in different kinds of applications, logistics and navigation, as I mentioned before, quantum chemistry and material simulation, and then finances and weather forecast. We are looking on different integration types, hybrid distributions and modular, that is top down and bottom up. We are looking at 6 different qubit platforms and different topologies where the connectivity and the error mitigation is running in a different way. And we try to compare the systems based on the needs of industry. So just to give you a feeling for the timing we are looking for. So we started with the Falcon F4 processor, 2020. Now we have the Falcon F4 and the cloud access, and we are going now to the Falcon R5 by improving the quantum volume. We will create the test and application center hopefully next year, and then we hope to go on by extending the contract with IBM to the more complex systems in terms of number of qubits and quantum volume seen or announced by the roadmap of IBM. In Germany, nearly all qubit platforms are investigated, and the quantum computer I have mentioned up to now are based on superconducting Josephson junctions. And I would like to mention only one more qubit platform because from my point of view, it's complementary, that are color centers in semiconductors. So we follow an idea of the Technische University of Delft, and we take a piece of perfect diamond and create color centers by nitrogen doping of diamond. And we use the electron spin and the magnetic moment of the electron spin, which interacts with the nuclear spins of carbon isotopes, which are intentionally or unintentionally incorporated into diamond. So we are looking at the 10 spin ensembles of magnetic dipoles. It's a kind of hybrid spin ensemble because we are talking about a combination of 1 electron spin and 9 nuclear spin. And what you have to know that we need a certain kind of coupling strengths between the spins. So the distances between the spins we are working with should be between 0.6 and 1.2 nanometer. So we are talking about a very small volume quantum processor or quantum register. And I would just pass the idea to you so that you see what we are talking about. So just to give you a picture of the operation, let's look at 4 magnetic dipoles which can rotate around the dotted line. and all the magnets are so close that they are coupled, because if you turn one, the other will turn two. And you see they're somehow entangled because the south pole and the north pole of the magnets is pointing red, white, if you go along the line. So what we do is, in principle, to couple and decouple the spins is we turn the spins by providing radio and microwaves by 90 degrees. And you can imagine by turning the magnet 3 that you can decouple magnet 2 from magnet 4. And that's what we're doing to create the gates created by the nuclear spins of the carbon isotopes in diamond. What we benefit of is the hyperfine interaction of the nuclear spins. And at the moment, we prepare registers with 5 nuclear spins and 1 electron spin. I gave you the publications, which I think are the best in the field, on the right-hand side. And the good thing is, because of the hyperfine interaction between the spins, you can address every nuclear spin with different radio waves, because they have different Lamour frequency because of their interaction. You need a kind of calibration because these frequencies are related to the piece of diamond you are investigating. So you have to, they are individual, you need a kind of selection. But if you do so, by example, Delft could achieve the system with 8 qubits already to create 1 register. And more important is, it's already demonstrated that you can make a 2-qubit gate. So what you see here is a sequence of Bloch spheres along an interaction between the nuclear spin in the field of 1 electron spin, and you change the angle of the spin state by radio waves and for the nuclear spin, and by microwaves of the electron spin. And what you see is that we are able to turn the nuclear spin by 90 degrees. And depending on the electron spin, if it's up or down, this turn is going to the right and turning to the left. And that is exactly what you need to create a 2-qubit gate. The advantage of these kind of spin systems in comparison to superconductors is that the connectivity and the coherence time is much better. The disadvantage is, because we need a sequence of microwave or radio frequency wave pulses to turn the spin state, is that the gates are relatively slow. So we have to find out for which kind of application this spin platform is the best. But what is good about it is that you can entangle the registers created by the spins by photons, and you can use it for distributed computing, because in principle, it doesn't matter where the registers are. As long as the light is able to couple the electron spins in the register, it will work. So just to pass the information for the scientists of you, what is good about it, you don't have to cool it the superconductors down to 50 millikelvin. 4 Kelvin is enough. Then we have a coherence time of a minute for 1 register, also in terms of minute for the 1-qubit state, and at least 10 seconds for the 2-qubit entanglement. And these are good numbers also in comparison to superconductors. And what we are going for in the next 5 years is to show that we can entangle the registers and make a quantum processor. So here the timeline is, we started to optimize the diamond. We can create the color centers. We can create the coupling between the electron and the nuclear spins. So in 23, we are going for quantum registers. Then we have to prove that we can entangle different quantum registers. If we do so, we will get additional funding, and then we push it to a quantum processor. And what we have to do in 5 years, we have to demonstrate 20 registers, 100 cubic systems within the project. And these kind of projects, as shown here for different qubit platforms, as I said, will start in Germany beginning next year, at least 8, which I know. So there is a big push in Germany, and we are looking for collaboration, because we promised so much what we have to do and towards going quantum computers. So any help from Switzerland, from France and Italy, whatever, is welcome. So coming back to the systems. So in the end, we are looking for distributed, net organized systems and cloud systems, because we would like not only to evaluate the qubit topology or the kind of qubits we are using, we also would like to look at the systems. What might be the best systems we are looking for? Is the quantum computer only a kind of accelerator for a classical system, or can we create distributed system with some advantage for user? Do we have needs for computer nets or modular systems, or is the cloud good enough? So by just looking at the big bunch of partners, and we are very willing to increase the number of partners with everybody, and with Switzerland, if they cannot get EU money, then let's go for bilateral projects. I guess we have chance to find the money if we have good reason to collaborate. I would like to thank the organizers for the chance to talk to you, and I'm open to questions. Thanks a lot.
Thank you very much, Oliver. Very inspirational, and for the audience, so those in the field, they know what you do, but for those perhaps not in the field, it's just amazing that things are now happening. These computers are there, and we can start to use them, and they are more and more being built. So this is amazing to see that we get to normal computers now to quantum computers, and it gets real. It's not only promises, it's something real.
Yeah,
so thank you, Oliver.
The system is real. There is an Eurostar, but it's not the fastest computer on the world. There's still a lot to do. But nevertheless, as I said, my feeling is, and that is my information to industry, if you're really interested, you have to start now, because you have to look for the right engineers, you have to look for the right people, and you have to find out what the system, the potential of the system might be good for. Maybe you have not to go full power. You can do it with partners. But if you wait to be sure that the investment will be placed at the right time, and you wait for 5 years, I guess you will be too late.
You're fully right. And you're right. I was referring to Rust, Europa Park, and you spoke about the Silver Star. I was more enthusiastic about the blue fire, because blue is Europe, fire is red, Switzerland. So we should collaborate.
Yeah.
So let's take some questions from the audience. So there is a question from Carmen Recchio Valcarce. It's a bit provocative. Can companies and institutions from Switzerland also make use of the system at Fraunhofer?
From the hardware, no problem, but from the contracts for the German universities and companies, Fraunhofer can decide about the access. For Europe, we have to ask IBM for permission. But by example, everybody might know Heike Riegel from IBM in Zurich. She would be a good person beside me to contact whenever there's a chance. As I said, there's no hardware problem. It's just export control and something like that. If there is real interest, we would push to do so, but I cannot promise that we have the chance to do it, but we can try.
Okay, thanks. Another question from the audience. Yeah, you ask for help from Switzerland somehow in your talk. Where can the Swiss help the most? What do you need from Switzerland?
By example, I would be very interested. By example, the University of Basel, only to name one, there are plenty more. They are going for the doped qubits in silicon, which we don't push in Germany at the moment. So by example, an exchange in the comparison, in the benchmarking between the qubit platforms to find out what is the best platform for which application, that would be, from my point of view, a good additional partner in the exchange and benchmarking of the system.
Yeah,
the different systems. Yeah.
Thanks, Oliver. And I think we have time for a very last question from Christoph Karl from Bayern Innovative GmbH. How will Fraunhofer ensure that generated IP will stay within Europe?
That was a long way to go, but in principle, the quantum computer in Eningen is the only thing which is seen by IBM US side is the identification number of the user. Anything else stays in Germany and is in Germany. So it's under German law. So that is what I can say. So it's the best thing we could do to make sure that if, by example, we have a quantum advantage and the companies start to simulate really something which is important for production and they don't want to share it, that we by contract make sure that this data stay on the system and are only seen by the company doing the programming and getting the results from the quantum computer.
Excellent. Again, thanks so much, Oliver, for your answer and for your talk. And we are going forward with the agenda.